Non, là c'est direct. Mais
Bon,
il y a
évidemment,
plein de
tu
gens
peux
qui
le
viennent pas.
garder après.
Et comme
Ah,
ça,
ok.
c'est facile. Exactement. Qu'est-ce qu'il a dit? Non, moi-même, je vais trop. Bon, qu'est-ce que tu dis là? Et bon, on va voir. Ti, 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 ti. D'accord. Bon, oui, je pense qu'ils vont arriver bientôt, je pense. Si. Ok, fait comme ça. Merci. Bon, d'accord. Et est-ce que quelqu'un peut fermer la porte, s'il te plaît? Merci. Bon, thanks to everybody for being here. Thanks to the jury. As everybody knows, today I'm going to present my PhD thesis that is named Reforming of Model Biogas Mixture at Moderate Temperatures over Nickel-containing Catalysts. This thesis was made by the direction of Maria Elena Galvez and Patrick da Costa, and is in the program of Sustainable Development Technologies from the National Council of Science and Technology of Mexico. This is going to be the outline that I'm going to talk today. In the first part, I'm going to present the general context. I will be starting talking about the CO2 emissions and the global warming. What is the biogaz? Biogaz upgrading to syngas, the thermodynamic equilibrium, and the reforming catalysts. After this, I'm going to talk about what is the experimental setup and characterization techniques. Later, I'm going to present to you the catalyst for the biogas reforming that we prepare in this thesis, and I will be ending with the conclusion and some perspectives. Well, to start, in a general context, we actually are know nowadays there is a problem about global warming. This problem is caused because of the accumulation of greenhouse gases in a general way. We have the nitrogen oxide, the water vapor, carbon dioxide, and methane. These gases are produced by the industrialization. And however, this problem doesn't look like it's going to be decreased, since the reports that we have every year indicates that we have a 2.7% of increase every year. That is concerning all the countries, the mainly industrialized countries, and they are coming together in order to have to sign some agreement to propose different alternatives to solve this problem or mitigate it. In general, this agreement are looking for new technologies, alternative ways to produce energy based on renewable sources. Among these renewable sources, we have biogas. Biogas is a mixture of different molecules of gases consisting mainly in methane and CO2. It's attractive because we have carbon in the composition, as you can see, and this can be transformed into syngas, that is a mixture of hydrogen and CO2, as you can see. Nowadays here in Europe we have a very high production of biogas. However, only 59% of this biogas is used for the production of natural gas, and the rest is just burned and discharged to the atmosphere. So that's why it's important to find a new alternative for the utilization of this gas. It's interesting because we have already methane and CO2 in its composition. as earlier I mentioned it, we can convert the biogaz into syngas. The syngas is important because from this mixture of hydrogen and CO2 and CO, sorry, we can produce hydrogen or synthetic fuels by the Fischer-Tropsch process and another chemical compounds. But the important thing here is what we can do to convert biogas to syngas. So the objective of this thesis is to do a reforming of this mixture in the presence of nickel catalyst. But this is not very easy since this process is very complex. We have plenty of reactions that are occurring at the same time. One of the first reactions that are present in this reforming or upgrading of syngas is the methane decomposition directly. We have hydrogen and carbon. But since in the biogaz we also have CO2, we can have the dry reforming of methane, and also we can have Rybert-Waters-Gachip reaction. And also we can have the split of CO2 at high temperatures, producing oxygen. Since we have oxygen, we can have a partial or total oxidation of methane. As you can see, all these mainly all these reactions are endothermic reactions, so we need to put in energy into the mixture to these reactions can happen. And also another important thing is we have a very slow reactivity in the absence of catalyst. So I did some equilibrium thermodynamic calculations just in order to see if these reactions is possible to happen. In the picture here, you can see that the main reaction that is happening when we have excess of methane, that is typical of biogas, we have the reaction of methane decomposition as the first place. So that is translated in the, as you can see, we have a high formation of carbon into the catalyst, so that may lead to the catalysis activation. However, we have a higher syngas ratio when we are using biogas. So as I previously showed, we have carbon deposition into the catalyst. What we can do is having reported that the oxidative reforming can decrease the carbon deposition and therefore decrease the desactivation of the catalyst. In this plot, you can see I forecast different percentage of oxygen in order to know what is the effect into the syngas ratio. We can see that as we increase the percentage of oxygen, we have a control of the syngas ratio values, and we are reducing the carbon formation. Theoretically, we have less, around 60% of carbon deposition less into the system by the oxygen system. Oh, sorry. Oh, fuck. Sorry. So as I was telling, so another alternative to in order to do this reaction is the reforming by using of the catalyst. So in this thesis, we select a nickel catalyst, since these nickel catalysts are reported to be available and cheap compared to the noble metal catalyst. This metal is able also to be deposited in clays and zeolites and layer minerals and oxides, and it presents also the possibility to be promoted by different compounds. The nickel catalysts, they were already used in the dry reforming of methane. However, as we know until this moment, we have an excess of methane in our sample now. So what we can happen when we are using this catalyst? So the main idea is to find and synthesize a nickel that will be active, selective, and stable for this reaction. Following, I'm going to present to you the setup that I've been using through this catalyst test. You can see here in a general way what is the manip that we have, the experimental setup, sorry, that we have in the laboratory. Coming from the thermodynamic equilibrium calculation, we are going to start testing the dry reforming of this sample, the increasing of the biogaz reforming, the methane in the biogaz reforming, and also the effect of oxidative reforming to see if indeed we have the decreasing of carbon deposition. And for the stability test, we set until 750 degrees. The reactions were made in a bed feedback reactor. We deposit here the catalyst bed. They were reduced in situ at 800 degrees. And the final compositions coming out from the reaction were measured by gas chromatography technique. Before and after the reaction, we are always interested in what's happening with our catalyst. So we were looking for some different techniques in order to know the properties as a reducibility of our catalyst, its morphology, the surface area that we can have, some basic acid properties that is present after the synthesis, the composition, and after the test we were looking for the carbon deposition, and also an important fact, the nickel crystal size and the structure. So knowing this, I'm going to present to you now the catalyst that I've been using in order to reform the biogaz. I started with this catalyst that is nickel hydroxide side derivative catalyst, and then I prepared nickel titanium alumina zirconia catalyst. I'm going to start talking about this first group of catalysts. In the beginning, I test nickel in this derivative catalyst that is mainly containing magnesium oxide and alumina. Then I'm going to present the results when we promote this catalyst with zirconia and ceria. And these two catalysts were tested under excess of methane that we know until now that is biogaz, reforming of biogaz. And then we tested in the oxidative reforming. So this catalyst, nickel containing catalysts that are total seed derivative catalysts, were selected because of it has been reported that they have basic properties. Also, they have the anion exchange capacity. They are very adjustable when we are introducing some promoters. And after the calcination, they present a very stable and organized structure. Plus this, previous work in our group in the laboratory was done, but just for dry reforming of methane. So that means we have equilibrium, equimolar concentration. So we wanted to know what is happening when we have excess of methane. These catalysts were prepared by co-precipitation method, and so we deposit the nickel in by this method. We have in the end this catalyst. For the promoter one, we introduce the zirconia and ceria by the absorption method. So in the end, we have these two catalysts, the one just with the nickel and the derivative zirconia hydroxide side, and the promoter one. So starting, we test the physico-chemical properties. Initially, we can see that these catalysts they are getting reduced at very high temperature, over 820 degrees. They are mainly basic. As you can see, we are also producing different basic side, weak, medium, and strong in all of the samples. The nickel crystal side is very similar, and after the ICP technique, we can see that the catalysts are containing around 20% of nickel, and they are mainly basic due to the high presence of magnesium. Talking about the acidity, when we are introducing the promoter, we have a promotion of the strong acidity. You can see here we are moving onto the strong acid size. and we have also increasing of the surface area. So we went straight to test what is happening when we are increasing the concentration of methane into the sample. We clearly see here that as we increase the concentration of methane, all the values are getting farther from the thermodynamic forecast before for methane and CO2. We have also here not very well quality of syngas, and so after this we wanted to test the promoted one. So we can see when we are introducing zirconia and serre, we have an increase in the concentration, so we have a positive influence of this promotion. However, we still haven't a lot of methane not converted. So now after this we are going to try to introduce oxygen in order to see what is happening in the oxidative results. We can see now that the excess of methane is getting converted in the samples. Also the CO2 is getting closer to the thermodynamic, and here the syngas, that is one of the main objectives for this reforming, is getting over the unit. So this is a very good result. Talking about the conversion rate, we have also even a increase of the conversions of the rate when we are adding the promotion and also the oxygen. About the carbon formation, we find that as the catalyst is active, we also have higher carbon formation in the sample. After this, we wanted to see what is happening for this catalyst through the time. For these two catalysts, we can see that they are a general constant. We have and about the carbon deposition, we did this 10 for the hydroxide nickel catalyst, and we can see that we have carbon formations that are taking also the nickel particles from the catalyst through their structure. And however, we are still having low concentrations, low conversion of methane. But until now, we already find that we can It's starting again. So I was totally sorry for the technical problems. I'm going to test this catalyst, and I will mix different supports about a binary and ternary system. Also, I'm going to test it in the same conditions for the excess of methane and oxidative reforming. So we call it nickel supported catalyst in the mixed oxides. Why we select this catalyst? Because this support, because titania, alumina, and zirconia have been very widely reported as amphoteric catalysts, since they can absorb CO2 and also they can activate the methane. We can also adjust these properties, and in the end we also have a very high stable property. These supports, they were prepared by Solgel method by aqueous solution of different butoxide, and we stabilize the solution at a pH of 3. After the support was prepared, we deposit the nickel by the impregnation method. So in the end, we are having 3 different catalysts. We did also the reduction after the test. The reduction by TPR shows that initially the temperature of the reduction is slower compared to the previous one. And the catalyst, the nickel crystal side, we have a variety, but this when we are using zirconia, is producing higher size of nickel crystal size. talking about the basicity, we are moving to the strong basicity when we have zirconia in our oxide. And about the acidity, we have a very high acidity when we are introducing alumina in the oxide. You can see here that the values from the previous hydroxide side derivative catalyst are very slow, so we are now having a very higher acidity in our oxides. Mainly when we are working with alumina. The alumina also is working as a enhancing in the we are also enhancing the surface area. After the synthesis, we wanted to see what is happening with the distribution of the nickel. Effectively, we have here very good distributed nickel in the support, and so we go there. We go later to the test. In this case, we are going to test the excess of methane, the oxidative reforming, and the stability test, all in the same conditions as before. Initially, we have the three catalysts prepared, and we can see that we have a very low conversion and any time. That also is happening when we have for the CO2, and the ratio is just getting over 1 on high temperatures. So we have no clear positive influence of the acidity. Also here we have we're still having low conversion of methane. We moved to the oxidative reforming, and we can see very clear effect of the oxygen. We increase around 35% of the conversion. In CO2 we are getting closer to the ideal equilibrium, and all the values are approximately 1. So feeding oxygen increase the methane conversion and approach the results to all the equilibrium. The best catalyst was the one titanium and alumina and nickel. So we tested through the time in an isothermal test. We can see that there is a slightly deactivation after 5 hours, and we can confirm that the nickel support are very good materials when we compare it to the previous one. That we have in this place we find in the isothermal in the previous catalyst. So these catalysts are promising for the oxidative reforming of the biogaz. Exactly as before I mentioned, as we have higher activity, we have also higher production of carbon deposition. The titania zirconia catalyst was the less active and a lower syngas yield. Another very interesting thing that we find that is the carbon that I just mentioned before is formed in a bamboo-shaped wave. So we can see in this for every catalyst we have all these very interesting kind of nanotubes, and we have a very slight sintering happening for the active phase. So we wanted to explain what is happening in the formation of these bamboo-shaped carbon nanotubes, and I propose here a mechanism for the formation of this, and it's mainly due to the quasi-liquid state of the nickel through the reforming reactions. In this place, you can see an example of the TEM for TN catalyst. So we find that this catalyst containing zirconia is the less active. So what we can do in order to promote their activity, so we find, as I mentioned in the beginning, these catalysts were prepared by salt gel method, so we can try to modify the pH during the synthesis. So in the beginning we have this catalyst at pH of 3 with a very big crystal side. In this step we are going to modify to 9 and 3 by different hydrolysis agents, being sodium hydroxide and nitric acid and ammonia. The first results shows that we have a lower reducibility temperature and we have very slow lower crystal size compared to the one that we prepared in the previous series. You can see they are less than 9 nanometers, and mostly when we are using a pH basic of 9. About the TPD of CO2, we have a highest basicity when we are using the acetic acid, and about the acidity, that is important fact for the reforming reaction. We have nitric acid and ammoniac are enhancing the acidity nature of the catalyst. You can see here in the table that all of them are very high values compared to the previous one, and there is no too big changes in the surface area between them. Moving to the oxidative reforming, we can see that the salt gel method allows to enhance the conversion from the previous one. We have here the previous catalyst, and all of them modified it are a higher conversion for methane and CO2 conversion. So this is, we can say that the problem was because we had too big crystal site and too strong basic sites. Also, we can see that there is a good compromise between the basicity and the crystal site when we are working with the reforming of biogaz. Same as before, as high is the activity, we have high amount of carbon in the after the test. As you can see here in this TEM, we have this very clear nanotubes. However, in this series of catalysts, we have a mixture of bamboo shape, as I previously showed, and now we have fishbone carbon nanotubes. We have a mixture of them. We found also a slight sintering of the phase, active phase, and the mapping, elemental mapping, shows that even though after the reaction we have a very well distributed phases. And another, we were thinking another alternative in order to enhance the behavior. So we propose another method of the nickel into the support. So in this part, I'm going to present you the surface redox method, having another series of catalysts to test them. We use the same binary and ternary system as the beginning and the pH of 3, but now the nickel was deposited by surface redox method. In the beginning, we can see that the reduction temperature is very slow, since this is correlated to the results of in this method. The deposition of nickel is happening in the hydrogen atmosphere, so the nickel that are deposited into the support is already reduced after the synthesis. So these peaks are just the remaining species of nickel in the surface. About the acidity and the basicity, we have a high acidity basicity when we are using alumina, and in all of them we are producing weak and medium kind of basic sites. About the acidity, we can see in all of them are increasing in compared to the other. However, the area is getting reduced compared to the other, but the main factor is that the acidity is getting higher compared to the other all materials that we prepared before. So this surface redox method, it mostly generate a very good formation of weak, medium, and a strong acid site that are promoting we can activate the methane. After the synthesis, we can validate also here the good well distribution of the nickel in the surface of the support. As a sample, I have here this catalyst. You can see the support and the surface. So we tested, and what is happening, we find even higher compared to the other, 20% of higher conversion. Finally, we are reaching the thermodynamic equilibrium with this catalyst, And the good thing is we are stabilizing all the values through the time in between 1 and 1.43 syngas ratio. So the loading of an activation of this catalyst of the nickel active phase has an important influence, as we can see. The conversions are higher compared to the other catalysts prepared by impregnation. As I was mentioned, the production of hydrogen is reflected into the syngas ratio. We found also around 10% of increasing compared to the impregnated catalyst. So here I'm showing you the stability test. In this part we have the best one from the impregnated. We have very slight decomposition, around 6. However, with this surface redox method, now we have just only 2% of desactivation through the time. So this method allows to have a very slight desactivation after these 5 hours. And they have very high conversion and as you can see, increase the stability compared to the impregnated samples, and also with the hydroxide derivative catalyst. We didn't find a sintering after the test, but in this case we find a very uniformly they are very uniformed on the surface, and even we have a very slight redispersion of the nickel phase. You can see, and the values calculated of the nickel crystal side after the test are slower. This suggests a very strong interaction between the nickel and the support as a consequence of this synthesis. We find also that the best catalyst was the higher carbon formation, and as I was mentioning, there is no sintering, or there is no proof of that. And in this case, the mainly kind of carbon nanotubes correspond to the fishbone named. And about the bamboo shape, there was no evidence in the temp characterization. I did a comparison between carbon formation and between the nickel support interaction. We can see here the two methods, and we find that we have nickel by impregnation. We have a very weak interaction between these two phases, and also we are producing bamboo shaped, as you can see, and I showed before, and that is producing also a nickel slide sintering. However, in the surface redox method, we have very strong interaction between these two phases and producing fishbone carbon nanotubes. And as I show you in the table, we have a nickel redispersion after this. And we conclude for some conclusions. For the first group of catalysts, we saw that we have a very low methane and CO2 conversion even when we put oxygen. They are producing also a poor syngas quality. However, we find a positive influence of zirconia and ceria. And these catalysts are mainly basic due to this ratio between the two oxides in their composition. Talking about the other group of catalysts, mainly we can say that the catalysts were containing alumina. They show the biggest conversion. This is due to the presence of the acid sites that may favor the activation of methane. As we saw, the titania alumina catalyst is the one with the poor activity, so we wanted to modify it by the pH in the synthesis. We saw that the pH of 9 results in better distribution of the nickel and also enhance the methane conversion. So the activity mainly is based in the good balance between the nickel crystal side and the basicity in their support. In the last part, we saw a new method of the introduction of nickel. We see that in situ nickel reduction leads to a stronger nickel in support interaction that leads to high methane and CO2 conversion for the catalyst prepared by this method, also mainly for the ones containing alumina. This method is allowing to increase the stability. We have lowered this activation, and we didn't find sintering. In a general conclusions, we try to reforming the biogaz, and this is involving working under excess of methane condition. As we saw, we need a catalyst that has to be selective and stable in order to do this reforming. We see also the benefit of using oxygen in the sample, in the feed mixture, to increase the methane conversion and approach all the values to the thermodynamic equilibrium. We find anytime carbon nanotubes after the test, and we promote the acidity leading to the methane conversion. We find that this is a very important fact to the methane activation. And finally, the sulfur redox method leads to more stable catalysts due to the increasing of the interaction between these two phases, the metal and the support. In this part, I'm proposing some perspective for the further work. Maybe we can do additional characterization to clarify the role of the interaction between the nickel and the support, and maybe we can find some mixture phases between these two elements. We could do further work to study the properties of the bamboo shaped fibers as an interesting carbon material, since we have always the production. About the properties of the material, we can quantify by pyridine the Brownstein and Lewis acid sites, and we can do the correlation between this and the conversion of the excess of methane. I'm proposing also here another support, titanium alumina, and we can prepare it at 9. As we see, this pH have the best results, and all the support that we use in this thesis, they are 50-50. So I'm proposing here different composition of this mixed oxide to see the behavior. About the carbon formation, I'm proposing here the addition of another metal as yttrium, as was reported to decrease the carbon formation.